All right, let's start with our lesson lecture. This is actually the last part of our whole course. It's about the intractability, which I personally find very, very exciting because now we start to look into a broader landscape and look into what sort of problems are fundamentally difficult and not solvable, and what sort of problems are actually easy. Right, so we are going to talk about the polynomial time reduction today, and perhaps if we have time, we also talk about the packing and covering. Right. So now let's really just get into the bigger picture. So far in this class, we have been talking about a lot of different algorithmic techniques, right? So we started with the graph algorithms, and then we talk about how can we do the greedy, and after the greedy algorithm, we talk about the divide and conquer, right? So how can you divide things into smaller pieces and merge them into a larger ones, right? So and then we move to the dynamic programming, which resembles a little bit of both greedy and divide and conquer in the sense that it's similar to greedy because we sort of have to build up some sort of recursive forms and then to make decisions locally. But it's different from the greedy because sometimes a lot of local optimum solutions that is done sequentially doesn't need to the global optimal. It's also similar to divide and conquer, right? So it's again that there's some sort of the you have a big problem, you divide into smaller pieces, but the difference between the dynamic programming and divide and conquer is that there are overlapping components between the pieces, right? And then we talk about the Maxwell mean cut, right? So mean cut, and then this is actually broadly fall into the very central notion of duality in in the combinatorial optimization. And if you are interested in this topic, actually there are a lot of similar things and related topics, related research problems that are in this area. Right. So these are all algorithmic techniques. Those are all the tools that we are helping to help you to really build up your skills to leverage these tools to solve the different types of the algorithm problems. Right. This lecture is really about trying to help you to understand what sort of problems are difficult, right? So it's really just the other way, the other side of algorithm design. Sometimes we need to design tools to tackle algorithm. Sometimes we need to be able to prove that some kind of algorithm problems are just fundamentally difficult and not solvable by any polynomial time algorithms, right? So here the very central notion is the so-called NP complete problem. If a problem is NP complete, it's highly unlikely that there exists any polynomial time algorithm to solve the problem, right? It's like we can only say that it's highly unlikely because the problem of the P versus NP is actually one of the very center open problems in theoretical computer science that has been around for at least 50 years, right? And a lot of computer scientists today do believe this kind of open problem still cannot be resolved within the next 50 years, right? There was a voting that was launched a few years back that asked a lot of theoretical some computer scientists about the landscape of this open problem, and a lot of them are not optimistic at all, right? So of course there are other problems that are even harder than NP complete, like such as the piece-based complete and undecidable problems, right? So some of these problems will be taught in the CS for 23 the automata course, right? So but for this course, then we just briefly talk about them, but we won't be able to spend a lot of time on it. Now, let's move to the classification of the problems according to the computational requirements. So the very center question we ask here is really just that: is there a unified theory that tells us that what sort of problems we will be able to solve, right? So the its original motivation is that can we solve all these problems practically, right? So can we characterize the problems that can practically solvable, right? So now, in order to answer this question, we sort of have to gradually build up a lot of theoretical models and works to properly encapsulate and abstract out this problem, right? So we come up with the notion of the Turing machine done by a guy that's not even mentioned here, and then we do recall that in the very early in our lecture we were talking about a problem is called efficiently solvable if we are able to design an algorithm that's running in polynomial time, right? So there's a theoretical definition of the efficiency, right? Um, it basically that means that it's polynomial time solvable in in the by under the Turing machine model, right? But we haven't been talking about Turing machine model for quite a long time, right? So you can also like is without like harming the very central message here. It's we can also substitute that by the word model, right? Word model is really just that can be solved by Python, right? So this is the what the theoretical statement is talking about, right? But again, that this is it's we come up with we start with a very high level abstract question what can be solved in practice. We try to use theory to sort of model this question and give an answer, but there's always a gap between theory and practice, right? So there has been a huge discussions on whether the notion of the polynomial time algorithm is really exactly characterizing those kind of problems that can be solved practically in the real world. And I did mention quite a bit of the rationales that's behind, right? So in theory, right? So if you have a n to the 100 polynomial time algorithm, is it really called efficient? It's very likely it's no, this is not efficient. But in practice, people do observe that so long as you manage to make an algorithm, a problem that's solvable by polynomial time, even the first algorithm is n to the 100, usually we are able to quickly push down this constant term to some practical numbers so that the algorithm can be used, right? So that means that in practice it's good enough, and that's the reason that we start with a ground and practical question and philosophical questions that can we characterize the problems that are efficiently solvable, and then we gradually move to a theoretical model and focus on this theoretical model. The polynomial running time algorithms will solve the problems can be solved by this kind of algorithms. Okay. So now let's be more concrete and just walk through those problems that people believe are polynomial time solvable, or just I think in layman's term that can be solved efficiently in practice, and those problems that we believe that cannot be solved by any efficient algorithms, right? So let's first start with looking at the problems that are polynomial time solvable, right? So we talk about shortest path, we talk about max flow, right? So and uh, and for the rest of the problems actually that is not covered in this algorithm class, you can maybe the two satisfiability we will be able to give you some exercise on that. But as you can see, like the topic of algorithm is a very broad topic. Even after the whole semester of studies, like we haven't talked about too much about the very exciting algorithms, right? So for two satisfiability, coloring algorithms, or vertex cover under the bipartite graph, or matching, all these problems turns out can be polynomial time solvable, right? So here one very interesting thing is that like there's a little cut over here, right? So anything above this line, basically those are algorithms that can be solved, that can really be easily taught in the typical undergrad algorithm class. And anything below this line actually requires a bit of research. Like researchers have put years of effort to try to understand this problem, and eventually they sort of figure out a lot of complicated algorithms to solve these problems, right? So I would just say that if you just study algorithm for years, you would just also agree with me that anything above this line is really just that if you use your intuition and just think that hard enough, you will more or less be able to figure out on your own. Anything below here, you need to do some research, and sometimes you will get a PhD degree with this kind of research, right? So here, like up to here, this is actually another interesting landscape or the landmark, right? So the linear programming, right? So it turns out that if we use the linear programming technique carefully, or we do a bit of the reduction, we are actually able to use linear programming to solve all the problems here, right? So sometimes they are directly, sometimes are not directly. Maybe not prime test, but a lot of the problems for those what I call the difficult problems in the difficult region, right? So, and if we want to sort of generalize the linear programming, we sort of have to, we sort of can come up with an algorithm that solves the convex program problem, right? So, and it turns out that this kind of linear program or convex problem, people have this very vague, right? Vague feeling, or sort of sometimes they have some sort of justification that maybe these are really just the most sophisticated algorithms that we as a human can design out under the current physical laws, right? So So there are some bold claims that any algorithms, if that can be solved, any algorithm problem, if that can be solved efficiently, then probably we can use linear program or convex program to solve them, right? So this is a very vague and probably it's not correct statement, but there are some sort of research that are pushing towards that direction, right? Is it really true that maybe at the end we as a human can just design an algorithm as difficult, as complicated as this one, right? This would be the set of the problems that are polynomial time solvable or just efficiently solvable. And there's also a set of problems that are not efficiently solvable, right? So for instance, if we, instead of looking into the shortest path, if we try to find the longest path on the graph, actually this is not polynomial time solvable. You sort of saw a question that are in the homework that tries to ask you to find the longest path, right? So most of you come up with the dynamic programming based approach. But here you need to pay attention that when I ask you to solve the longest path problem, we sort of assume the graph is a DAG, right? So in general, if the graph is not a DAG, then all of a sudden it becomes very difficult. Right. Also, if we want to just solve the mean cut problem, it's pretty easy because we sort of can use the max flow algorithm. But if we want to solve the max cut problem, right, I want to be able to chop this graph into two pieces so that the number of edges that are crossing crossing these two components are maximized. This is called max cut, and all of a sudden this becomes also very difficult. Right. So the satisfiability problem, we are going to talk about that, right? But later. But here you really just need to pay attention that even for the same set of problem, right? So basically, satisfiability is a family of problems whose difficulty is characterized by a constant number, right? So you can talk about 2 set, 3 set, and then 4 set, right? So the k here, this 2, 3, 4 here is sort of a parameter characterizing how difficult or how complicated this problem is. And it turns out that when you change the parameter of the same set of algorithms, all of a sudden the same set of problem, all of a sudden it moves from solvable to unsolvable, right? To solvable to unsolvable, right? So again, like the colorability has also the same issues. If you want to check whether there's a graph, a planar graph that can be colored using 4 colors, then it's solvable. Actually, if you look at the map, right? So if you look at the global map, right? So just imagine you have a map of the whole world, right? So basically each country is using a different color, right? So there's a theorem that says that if you want to color the map to make sure that if two countries are next to each other, they use 2 different colors. There's a 4 coloring theorem says that you need at most 4 colors to color all the map, right? So 4 colorability algorithm just has been widely used to color the map. But then there's a question that is it possible to color all the countries using 3 colors? Sometimes it's possible, sometimes it's impossible. But what's very exciting, is even a bit, perhaps also a bit surprising, is that actually deciding whether a map can be colored using only 3 colors all of a sudden becomes computationally intractable. Right. So again, like if you work on a bipartite graph, you want to find the cover. Like for this cover is also what we need to talk about next. If it's a bipartite graph, it's so easy. And if we just want to work on the general graph, all of a sudden it becomes difficult, right? So we can see a lot of this kind of things going on here. So long as basically another very high level message on this whole table is that sometimes you just tweak the problem a little bit, all of a sudden the problem becomes much more difficult. Right. So this is one of the key message in this. So now let's continue our discussion. So again, right. So a very bold objective of the theoretical and computer science is to really just to classify all the problems into those that can be solved in polynomial time and that cannot be solved in polynomial time, right? So we have been talking about a lot of algorithms that can be solved in polynomial time, right? So let's really just draw some Venn diagrams to illustrate this idea. This is polynomial time solvable, let's call that P, right? And so we are going to talk about a lot of problems that we believe is going to be harder than the polynomial time solvable, but it's really just that it's one of the major open problems, right? So but there's also a question that are there anything that's obviously, right? So if I draw a diagram that looks like that, right, it's all a very abstract description. If the problems are at the bottom, they are the easy problem. and then if the problems are the top, they are the hard problems, right? So we do have this question that, of course, like there are, we already acknowledge the fact that there could be a set of problems that are very likely to be difficult, more difficult than the polynomial time solvable problems. But are there any problems that are known to be not polynomial time solvable, right? So we also really just want to sort out the landscapes, and the really high level idea is really just to navigate sometimes it's a bit randomly, just to make sure to understand what sort of problems we can what sorts of questions we can understand, even simple ones, right? So one of the very simple question is that, oh, okay, so can we really identify some of the a subset of problems that are known to be not solvable in polynomial time? And then it turns out that there are this kind of problems, right? So there are, like here, the lecture notes give you 3 problems that are known to be not solvable in polynomial time, right? The first problem is that if I give you a C++ program, like that has constant number of lines. Constant means that you really just write down the program and stop, right? You never change the program. It's a piece of code, right? If I give you a piece of code, and I ask you to determine whether the code can be hot in at most the k step, right? So basically the question is that does it insist a certain input to your program, right? So when we talk about a C++ program, we assume that there's an input to this program, and the question here asks you that are we able to identify the input to this program? Like for instance, your program is doing a sorting, right? So or doing something that's strange, right? So if I give you the program as a black box, can you find the input to this program such that the program halts or just completes its computation in at most the k step? And it turns out that this algorithm probably needs to be solved in polynomial exponential time, right? So this is actually a pretty abstract problem, right? There are also some more natural problems that are also provably requires exponential time algorithm, right? The second problem is that if you give you some sort of ball games, right? So a lot of ball games has these properties, right? So say if I have a generalized version of the checker games, are you able to determine that which side of the players is guaranteed to win, right? So what do I mean by guaranteed to win? So if you look at all these games carefully, right? So all the entire game has the deterministic state, right? So theoretically, this is really just theoretically, if you have sufficient or infinite computation power, you can also exhaust all possibilities of your moves and your opponent's moves. So the entire game is deterministic. So theoretically, if you have a lot of computation power, you can actually determine who is going to win, like in advance, even before the game. But in order to determine that, it probably requires you an exponential amount of time, right? So these are actually two very, I guess one of the two very well-known problems that are probably to require exponential time. But but here I'm just giving you the examples, right? Even to prove the statement we are making here is going to take a substantial amount of effort, right? Right. Right. But as I mentioned, right? So we sort of know a set of problems that are provably solvable efficiently, and the set of problems that are provably not solvable efficiently. What's most frustrating is that there's a huge number of fundamental problems that actually lies in this unclear region. It's unclear that whether we are able to solve the problem using polynomial amount of time, right? Right. So now. After this background, then we start to get into the notion of the polynomial time reduction, right? So the high-level idea works like that, right? So let's start with a particular problem, right? So let's say that we want to say the color graph, right? Color graph basically means that if I give you a graph, are we able to color all the nodes are we able to color all the nodes using different colors so that if I look at the two nodes that are connected by the same edge, they shouldn't share the same color, right? So I'm going to elaborate this problem a bit later, right? But the high level idea is that, like let's say that we start with a problem, and the researchers has been working on say 50 years to try to tackle this problem and has not come up with a solution a solution to solve the problem, right? So now in practice, like we sort of believe this problem is hard. really this problem is hard, right? So under this kind of belief, are we able to talk about that whether another problem, right? So let's say that when you do the machine learning research or you do your biological research, you come up with a new problem, right? So obviously, when you look into the new algorithm problem, it looks harder to you, right? Then there's this kind of question that, well, if you look into this biological question, it's hard. Is it just because you are undergrad, you don't have enough experience, so that you cannot design a good algorithm, or is it fundamentally hard, right? But because it is a new algorithm, probably you won't just get the same sort of privilege as the coloring problem that attracts a lot of scientists to study its behavior, right? You just cannot, right? It's really just infeasible to spend another 50 years to try to understand whether to put the best effort to understand whether there's indeed an algorithm that can solve this problem, right? So, but then we still want to be able to talk to sort of give some evidence on maybe the new biological problem you are solving is harder than it's also hard, right? So the way people establish this kind of argument is that, so let's try to build up what's called a reduction, right? So the reduction at the very high level really intuitively looks like that, right? Just assume that if you have a black box that can solve the problem that's on your hand, the biological DNA sequence problem that's at your hand. Then, and on the other hand, if we are able to somehow transform the graph algorithm, the coloring problem into a problem that can be solved by this black box, and indirectly solve the coloring problem by using this black box, then basically we can sort of claim that, wow, this black box is so powerful, it can both solve the biological problem and the coloring problem, right? So that also means that the coloring problem, the biological problem is at least as difficult as the coloring problem, right? So the logic is like that. If my solver can solve the biological problem, and I can also use the solver to solve the coloring problem, that basically means that the biological problem is going to be a lot harder than the coloring problem, right? This is the high level logic over here, right? So now we're going to really just formulate and articulate the definitions we're going to head towards to.